Hello, this is Dr. David Kreller of the Department of Chemistry of Chulalongkorn University in Bangkok, Thailand. I'm here with another video lecture. This one is about the contents of Chapter 8 of the chemistry book by Raymond Chang and Kenneth Goldsby. The title of this chapter is Periodic Relationships Among the Elements. I'm very happy to make this video to support the education of my students in the class General Chemistry 1 at Chulalongkorn. But I will put this video on YouTube, and I'm very happy if other chemistry students elsewhere in the world can find this video and learn something from it. I'll start by saying that although this chapter is Chapter 8 in the Chang book, which has titled Periodic Relationships Among the Elements, I will say that this material is very, very similar to the material in Chapter 7 of the book Chemistry, the Central Science, which is written by Brown, LeMay, Burston, Murphy, and Woodward. And this chapter 7 in that book, is entitled Periodic Properties of the Elements. I admit that many of the graphics and the materials used in this video presentation come from the publishers of that book, Pearson Prentice Hall. Okay, we'll get started on this interesting content. There's some properties of atoms that are controlled by electron configurations. Those properties are sizes of atoms, ionization energy, and electron affinity. So we'll discuss what those properties are and illustrate the fact that there's periodic trends in these properties. But first, to understand these properties and how they depend upon electron configuration, we should review electrical forces. Because if you want to understand the aforementioned properties, because they depend so much on electrical forces, you should understand those electrical forces first. And the electrical forces within atoms are the attractive forces between the nuclei and the electrons, and the repulsive forces between electrons. Okay, let's review electrical forces. Try to imagine two charged objects that have an electrical force between them. Of course, here we have a picture of charged object 1, charged object 2, with some distance between them. We'll call R short for radius, R1 to 2. And here's some sort of interaction occurring between them. What controls the size or magnitude of that force? You may have studied this Coulomb's law. First, what determines whether the force is attractive or repulsive? Of course, are the charges, the signs of the charges. And the magnitude of the charges control the size of the force, as well as the separation. So here's Coulomb's law, kind of boiled down a little bit, to show the relationships between the charges and the distance and the way that they control the force. Directly proportional to Q1 and Q2, and inversely proportional to the square of the radius. Let's look at the electron nucleus attraction. Here's a nucleus with some charge, Z+, which depends upon the number of protons that are in that little bundle, and interacting with the electron. Of course, because this has a positive charge and this is a negative charge, there's an attraction between them. What controls the strength of that attraction? The size of Z, actually, the size of the charge in the electron is not variable. All electrons have the same charge, but different nuclei obviously have different charge based on the number of protons there. So that's one variable that controls the strength of the attraction. And obviously, the larger Z, the more protons in the nucleus, stronger will be that attractive force at a constant separation distance. But the other variable, once the charge on the nucleus is specified, and we know the charge on the electron, of course, the other variable is that separation. As that separation increases, the force decreases according to the square of that distance. So that's a quick review of electrical forces. So we've discussed the basic electrical factors that control the size of the electrical force between electron and nucleus. Now let's talk about, I guess, those factors in terms of the orbital properties. So n is one factor. The principal quantum number of the electron, of the orbital, I guess, that the electron occupies. And Z, or Z, effective, the effective nuclear charge felt by that electron. So in this figure, we're looking at the stabilities of electrons. These are three atoms which just have a nucleus with one electron. And in each case, the electron is in the 1s shell. And so in each atom, the electron is in the same 1s shell and hence exists at about the same distance from the nucleus. So this factors out nucleus-electron separation variable. So all we're looking at is, I guess, the strength of the force of attraction between the nucleus and the electron, and the way it depends upon the charge on the nucleus. So if we start up here, it's just a one positive charge, one proton nucleus. Compare that to that one electron orbiting around and being attracted to the two positive charge on the nucleus, and now also the three positive charge on the nucleus. And on this axis, the energy axis, you can see the stability of those electrons, I guess. You can look at these numbers and say how much energy would be needed to pull those electrons away from the nucleus. The electron is much, much more strongly attracted to the nucleus when it's attracted to the nucleus with a three positive charge. And obviously this would be a much harder system to ionize. So on this slide, we just took a quick look at the effect of varying the nuclear charge. And we see that the higher the nuclear charge, higher the stability, or the stronger. Now, let's look at the effect of electron-electron repulsion. So we're, again, comparing the stability of electrons in different types of atoms. And here, we're looking at, I guess, helium atoms with just one or two electrons in them. When the helium atom just has one electron, it's helium-2 plus nucleus, of course, but that one electron is all by itself around the nucleus. We're comparing that to this situation where, again, we have the helium nucleus, two positive charge, but there's two electrons. And actually, they're both in the 1s. So this would be 1s1, this would be 1s2. Now let's look at the stability of those electrons. When there's two electrons there in the same orbital, each of those electrons becomes a lot less stable, higher potential energy, easier to ionize, because there are electron-electron repulsions that destabilize it and lift it up to a little higher energy. Now the next comparison we'll make is in lithium atoms. And we're going to compare a lithium atom which has all three of its electrons to a lithium atom which is in kind of a weird state. Imagine changing it so that we just take away the two electrons that are in the 1s shell, but we leave the one remaining electron in the 2s shell. Obviously, this is a very unstable situation. That electron would fall down to a lower energy if it could. But these numbers, which have probably been calculated by quantum mechanical methods, show the stabilities of that outermost electron, or the single electron. Actually, I guess in the case of lithium-2 plus ion, you'll see that the electron that does not have the two electrons between it and the nucleus is much more stable, much more stable than the electron that does have the two electrons in that inside shell that resides between it and the nucleus. So we're looking at the effect of inner electrons. And inner electrons protect the outer electrons from the nuclear charge. You could say this nucleus gives off a certain amount of charge, field, radiating into space. These inside electrons kind of block some of that charge. It takes approximately 6 times more energy to remove the electron when there's not the 1s electrons there than when there are. Now, what is effective nuclear charge. As we've mentioned, or in a many-electron atom, electrons are repelled by the other electrons, as well as attracted to the nucleus. And we basically said this in words on the last slide. Due to the electron-electron repulsion, the electrons don't feel the entire nuclear charge. So the nuclear charge that an electron feels we'll call the effective nuclear charge. And that's always less than the actual nuclear charge. We're using here as an example of this sodium atom. One valence electron outside in the 3s shell, and 10 inside electrons, inner electrons, the lower principal quantum number of 2, between it and the nucleus. And that inside shell is essentially the same set of electrons, the same electron configuration as there is in a neon atom. There's a quick and easy estimation of effective nuclear charge. It's basically the atomic number, or the entire charge, 11 in this case, minus the number of inside or core electrons. That would be 11 minus 10 is 1. Would be the effective nuclear charge felt by this outermost electron in the 3s shell. And here's a picture, electron density map for the electrons. And this indeed shows that that inner core of electrons, which has a lot of electron density, right, because there's 10 of them, lies basically inside the orbital for that 3s electron, which is kind of complicated, of course, because it's a wave function. The location at which the 3s electron spends most of its time is farther away from the nucleus than the location of all those inside core electrons. So they are said to shield that outermost electron from nuclear charge. It's a really beautiful analogy for shielding. Analogies are great sometimes, but we can't take them too far, take them too literally. But sometimes they're very useful. This is a useful analogy. Imagine you have a light bulb which is giving off radiation, and the radiation given off by the light bulb is observed by this observer, this eyeball. But the total amount of radiation that makes it all the way to the observer is also controlled by how dark or thick is the glass that lies in between the observer and the light bulb. The more frosted glass there is between the light bulb and the observer, the less will be the radiation that makes it to the observer. Now, I'm sure you're a very intelligent and very bright person, and you already see the analogy. The analogy is like this. The light bulb is kind of fundamentally like the nucleus. The light bulb giving off radiation is like the nucleus, which is giving off a field of the positive charge. The observer is like the electron, the outermost electron that we're considering the forces on, and it feels attractive force based on how much of that positive electric field from the nucleus makes it all the way out to this electron observer. But of course, the frosted glass is analogous to the inner core electrons. Just like the frosted glass blocks radiation from the light bulb, the inner core electrons block the electrical charge that the observer feels. Cool analogy, huh? Thanks for watching this video. Thanks for sticking with me. So what have we done? In this video, we have reviewed electrical forces in atoms. We reviewed the factors that control the sizes of those electrical forces. The factors being the size of the nuclear charge, and the separation between electrons and nuclei. And we have done some nice work together to understand what's called screening in atoms. In the next video, we're going to talk about periodic trends in atomic size, ionization energy, and electron affinity. We will see that we can nicely explain and understand the trends in these three atomic properties in terms of the sizes of those electrical forces within the atoms.